You see the titles, but K there will not mean what it meant in the talk before, so it'd be a little more general.
First of all, I wish to say something that parameters for speed. Here, second of all, I really say some words about G and K. How it can just kind of explain why it's difficult to me on work on this topic. So, somehow starting approach is the approach with transformer model and reductivity property, which is extremely significant. So, if you really try to check what does this condition mean, to be a transformer model and to get an initial transformer model, you need to figure out that really for these conditions, it's not so significant which pair of reductive algebras G and K you really take. You could just apply these conditions. And then you could try to think, so does it make sense for non-symmetric pairs? Does such models exist at all? How much such models exist? And so on. And somehow this is a basic idea of what I'm doing. Okay, now let me provide corresponding definitions. So first of all, I fix some G model. I fix reductive algebras, find dimensional reductive algebras G and K. Reductive specificity over C. And fix some G models. Then I say that M is a G model. If M is a direct sum of simple finite dimensional G models. You guys are G models. Okay. Then I provide a definition which really corresponds to an infinity curve. So we could present M as direct sum of all possible simple models over K, and just group this sum, group the sum by their multiplicities. So we say that we sum up 2 times this model, 3 times this model, and so on. And if all these multiplicities are fine, so any given model that participates in some defined degree time, then we say that this model is admissible or finite. And so the definition is bounded. All stations is 0 is the constant, and that all the multiplicities are smaller than this one. Okay, so now I need to say some general words about this definition. So first of all, for a generic pair GK, such models of finite type or admissible are studied by Penkov, and Latif, and they really show that the majority of pairs G and K really have such infinite dimensional model of finite type or admissible. And such models are considered by Penkov and on the contrary, they show that if at least one such model exists, then there should be a quite strictly always satisfied for G and K. most pairs GT really doesn't have even one same model. It bounded infinite-dimensional model, but have really a lot of admissible models. This is kind of a general remark, and now I prefer to provide some examples. Say, example 0 is kind of what you recall an example of a homomorphic functions on disk, on which S of 2 are X with action of S of 2 R. And the maximal compact subgroup is really X, and then just want to reduce the action to the action of the algebra S of 2 R, and the action of a maximal torus on the algebra, say the same example. And this function would be bounded as to RT model. Okay. I provide several other examples. One is that we consider action of group SOM on Cn working integration of Cn. This action has an open orbit with no dispute. And one would consider just functions on this U. And then I claim that these functions on U are in natural way SLN, SOM model. So here the action of SLN is kind of clear, and now we should just provide it with an action of the algebra SLN. The action of the algebra SLN comes from the following construction. There is an action of SLN on Pn-1. And this provides us a map from SLN to vector fields on Pn-1. And we will apply any vector field to any function, and if we have a function which is regular on U, and apply it to some regular vector field, then we apply again some function which is regular on U. And this provides us really an action of Lie algebra SLN on this vector space. And at the end, just we have that this guy is an SLN model, and it is easy to check that this SLN model would be bound. And kind of non-complete example number 2 is that there are several symmetric pairs of three algebras such that any simple model for this symmetric pair would be a bound model. Maybe we could consider
first example, maybe you don't have dimensions, right? SLN, GLN plus 1?
Yeah. So it seems to me that any simple SLN GLN plus 1 model would be bound as GLN plus 1 model.
How does GLN plus 1 say this other?
Oh, wait a minute, yeah.
Okay, that's all I know.
So, if you believe that there exists enough Qaisar models for any reasonable pair of Lie algebras, then just for some of these pairs, these models would be just automatically bound.
Not necessarily multiplicity wanted because of the last example.
Yep.
Last example, they're all bounded.
In previous examples, all things would be bounded really by unit. But usually you would apply the following construction. You could take, say, 5-dimensional SLM model and multiply it by your model of multiplicity unit. And usually just, okay, new model wouldn't be really simple, but it would have a lot of some simple constituents, and these constituents would have finite multiplicity, but not necessarily unit.
Yeah, but that of course is cheating. I mean, you wouldn't ask for multiplicity 1 unless it's simple.
But one doesn't.
Well, I mean,
So there are two different models which have different supports, and then some of them would have still multiplicity 1. Okay, so now really just it's kind of a framework, just basic definitions, and I want to provide kind of method by which I prefer which I can use to study this subject. Namely, just if we have some G model M, we will define this some joint invariants. Namely, the first one is right of it, which is the summary of the star. To be precise, there is kind of not so complicated construction which shows how one constructs this variety, but I really don't believe that it runs much. It's more kind of, base properties of it, and then you would do something. And now I prefer just to say that it exists. And for any G model, you can also assign a methylator with. And this manipulator also would have some variety, which also lies in the star, and there would be a natural conclusion. Okay, so this is kind of just joint invariants which I use to study this stuff. And now I try to translate this notion of GK model, of admissible model, and of bounded model to the language of this varieties, and this was the variety of ideal I. Namely, so if M is a GK model, okay, first of all, I wish to note that if you have a reductive V algebra G and K, we really could assume that these V algebras are in a natural way V algebras of some groups, and there with the corresponding embedding of a group K into group G. Okay, M is a GK model, it really implies that DSM is preserved by K. This is kind of more sophisticated condition. So, any K, if and only if any K order of DSM contains 0 in order. And such condition is translated as M is bounded if and only if D of M is 0. This condition I really understand in the following way. So we will fix some words about the right B of K, and this condition means that B has an open orbit, K has an open orbit on any irreducible component of the open.
Excuse me, Alexey. The Vietnam, it really lives in the dual of the quotient of G by K. Is that correct?
But you can construct. Okay, this is true, but there is an embedding of this guy into this guy. really wish to say more about such models, but to do this I really have to be a little bit more specific. So I wish to say that G should be isomorphic to SLM. In some sense, one could really repeat similar arguments, trying to do similar stuff in other cases, but it's a little bit more. Okay, let's assume for now that G is SLM and what we can say in this stage, and moreover, of course, I assume that M is not only a G model, but is a simple G model. We have M, we have I, we have D of M, we have D of I, and that is good. Okay, in case of SLM, and taking into account assumptions that M is simple, we have that D of I has to be a closure of some nilpotent coadjoint orbit. It is well known that in each SLM, all nilpotent coadjoint orbits are reduced. And this really means that this D of I is kind of decentralized or directly isomorphic to the corresponding bundle of some flat variety of SLM. And it means under this decentralization, D of M really has to be decentralized by some co-normal bundle to some subvariety of this flat variety. So this is M variety. And as inside here, okay. Now let's try to repeat similar description of both of just GK model, a distal GK model, and bound GK model in terms of this S and so. So, what does it mean that M is a GK model? This really implies that our variety S is preserved by K. What does it mean that M is real? So, really, it's not so simple to describe what really that means, but one could really figure out that this really means that S belongs to some not so easily describable finite with varieties. Some varieties attached to G and K. Okay, and really the last condition is kind of simpler than the previous one, and it's kind of a general station. So here we just impose much more strict condition on our model. And so the corresponding models and the corresponding categories will be much simpler. So M is bounded. Would be spherical. With respect to action. So just now I just want to mention that for normal bundle to a variety inside the variety has the same dimension with base flat variety. So it's not so surprising that, and what does it mean that some variety is spherical? It means that the Borel subgroup has an open orbit on this variety. So we have two varieties, on one of them we have an open orbital subgroup, and it's not so surprising that if one will have open orbit, then the other one will also have. So this variety is spherical if you want to one variety it is kind of a theorem due to okay, so just what's really happening? We start with a problem of description, just studying bounded GK models, and then we just try to stop on some given case of SLN, and it turns out that if we have some bounded epsilon k model, then just there is some flat variety which is spherical with respect to action of k. And really, just this geometry problem is kind of interesting by itself, and I spent some efforts and some time and produced some joint paper with Roman Kiev in which this problem is solved completely. Okay, let me try to explain what is the role of just this answer and just this word in the description of bounded epsilon k models.
Can you state the problem exactly that is solved by
I just repeat once more thing. Okay, let's try to describe how the classification of all bounded epsilon k models should look like. Such classification is not easy, but we can provide kind of steps, and I say that 2 out of 3 steps are yet done, and 1, so just I have to think more. One has to describe classical varieties of the manipulators of bounded models. Second step, one has to describe manipulators themselves. And it's kind of a combinatorial problem which is, say, known for last 7 years. So if you have some nilpotent coequilibrium in SLN, which two-sided ideal have this given associated variety. It's not completely trivial, but there are papers where it is described. And third problem to describe ideal to describe GK models in our and related by any given ideal R. And it turns out that if your model is manipulated by such an ideal, then it is necessarily bounded. So just what does it mean to describe such nilpotent coequilibrium? Any nilpotent coequilibrium is really if bidirectionally isomorphic to some class of flat varieties, to the cotangent bundle of several different flat varieties. And this associated variety is suitable for our purposes, so just it corresponds bounded models if and only if at least one and if one than any such flag varieties say are spherical. This guy has to be spherical. And describe such spherical actions on flag varieties. We describe such key spherical actions on flag varieties.
So is K fixed in terms of you take an arbitrary K or a common?
So somehow we try to describe all such pairs as LMK. When not even pairs, so we consider trivial SLM, K, and flag variety. And thus, whether or not K acts spherically on this flag variety. And it's possible to describe all such triples, SLM, K, flag varieties, such that this action is spherical. Okay, and then just I could say that this is kind of dumb. This is kind of simple from 1 after you really do 1. And here, just one has to think more. Okay, and after it, I really wish to show how one could realize all these questions for some given pair of GK. In a sense, just how the final answer for such a problem could look like. I consider the following other key. I consider GLM. And I got this GL and divided by 2 via the omega 2 omega. And then I embedded this the algebra into SP and multiplied by n-1 and call it G. So what is the number for function? So what is the possible fixed varieties of respective ideas? It turns out that in this case, for the bounded model, the possible fixed varieties is coincide with orbit of the highest wave vector. And this is only spin. So, I'll do it. It is well known that for such a variety response just 5 years. Such ideals are described by Joseph 30 years ago. So the answer is Joseph ideals. Okay, and what is the answer? And what is the answer for such question? So how to describe all models which are manipulated by this given Joseph ideal? The answer is kind of the following. So if you try to consider this quotient, it turns out that in some case, this quotient is just isomorphic to some Fourier's algebra of differential operator of Weyl. And then the representations of this algebra would be really equivalent to representation with resource algebra of vector. And after that, it turns out that really representation of this function is really equivalent. Figure of GT models interrelated by this Joseph ideal really equivalent to figure of reverse sheaves on S2C and with respect to simplification by JLM and this JLM simplification. So just symmetric matrices up to conjugation. JLM simplification and here we have to consider reverse sheaves with respect to simplification. There is people who really describe this procedure. Mainly there is the work of Bremen and Wenger. Year 86. Okay, so yeah, thank you, Max. In which they describe the figure as a figure of representation of some Weaver with relations. Some explicitly given Weaver with explicitly given relation. And somehow I consider this as a final answer for this layer of GT. And I believe that it's possible to work out via similar machinery answer for all other field collections and subgraphs. And there is kind of a list of them.
So the category of bounded blocks is this category?
It's little blocks. Any block, one block corresponds to one Joseph ideal. And any such block is equivalent to consider representations of some explicitly given Weaver with relation. I think that's all.
You sure? Okay. Questions or comments? All right.
Just trying to parse what you read there. So, via is the orbit of the highest wave vector of the group SP2N.
So let's see.
Yeah.
So let's see.
This is a
So
quadratic
the highest wave vector in the algebra.
This is a quadratic residue.
Yeah. So this is how you construct the Joseph ideal. You go backwards from this to an actual ideal.
Any other comments?
And do you use, so Joseph has an explicit formula for I. Do you need that?
Really no. He just write down all possible highest waves, and he shows that just a figure of models which are manipulated by this given Joseph ideal are equivalent just because of translation principle. And then it is clear that translation principle preserves the figures of GK models. So if you describe the figure of GK models manipulated by one Joseph ideal, you could just say that all other blocks which are manipulated by other Joseph ideals are equivalent.
Okay, so are you saying that all the modules are related by the translation principle? So they're all regular infinitesimal character?
Second, all characters corresponding to Joseph ideals in case then are single regular.
You remind me what that means.
So it means that, say, you can represent the highest weight for SPQN just by n numbers. If they all are integers, your character is integer. If they all are semi-integers, your character is semi-integer.
But they're not necessarily regular with respect to the volume. With respect, no, that's not.
Okay, then just.
I'm asking.
I think it doesn't matter really. So
I'm
just
asking a
very one.
technical question, but you tempted me with the translation principle. We can discuss.
I think quite some rate per sheets come into the third part.
Mm-hmm.
So just if you consider somehow all Joseph ideals in this universal development algebra of SPQN are kind of equivalent to translation trees. So quotients of them are really equivalent. And just for one of these quotients are just Qaisar with differential operators which has even degree in differential operators of even degree of n variables. And then just one to easily check that really representations of this quotient which are GLN equivariant are the same as representations of the whole differential operators which are GLN equivariant. And such GLN equivariant representations of differential operators of S2 of Cn are natural way equivalent to just reverse shifts on S2 of Cn. Just by standard mechanism dimension. So somehow just apply something which is known for 50 years.
Okay, any more comments? Could you maybe just give a small example in which this could be made a little more explicit?
We will doing more details, example with action of S and N on in N-1. So just here,
Well, that's quite a general one case, right?
but it's not a interchangeable model is bound.
Okay. Can you do that?
Say, just really this U would be just isomorphic to, so we have Cn, we have a bilinear form, say, just bring it up and say F, and then say F equals to unit would be isomorphic to U. Hypersurface is defined by F equals to unit would be isomorphic to U. Then we consider functions, and these functions would be just described quotient of defined by F. And it is kind of clear that just all highest that this guy as an SON model would guys want to just where the sound on the line.
So here the K is SOM.
Yep.
And the G is
SON.
SOM.
And then there is just for SLN?
For G of the.
Right, so for the other,
We have an idea how to do it, but they work with SLM submitted on our pack and work with other types just in progress.
okay, but you intend to finish this, right?
Yep.
So this would finish the first step, right?
Yep.
But then you would also finish the second step, because as soon as you know for the answer explicitly for all the other series, you probably will finish the second step. Right?
Yep.
And what about this conjecture or question that we have? So you proved, which you didn't mention, but we felt that this was accepted a couple of years ago when we studied that if a pair GK admits a bounded infinite dimensional GK moment, simple, then it admits a multiplicity free moment. And that is a corollary rule for SLN. Well, yeah, I'm wondering whether now we could get closer to the answer whether this is correct or wrong for other types. Well, do you think that?
I think that for classical algebra, I kind of just should make an important proof, but in other cases.
Well, there might be something going on in the series which prevents this.
So,
anyway, this is still. So when you finish this work with them, do you think that this will be done? Get the answer to this or
No.
All right.
They are kind of just a little bit different area, because here you have to do something with the smallest non-positive organisms and with Joseph's ideals. And just Roma doesn't very well with the whole.
Okay, so then it's still a question of whether if you have a bounded, you can look at the multiplicity. Then,
So just a question, I mean, in either way of the question, spiritual business, you take a closed orbit, you look at the normal bundle, look at the compact mesh on the normal bundle, which should be easily computed by a five-dimensional representation theory, and simply check if the generic orbits are coisotropic in the normal bundle. This says if they are, if and only if the normal bundle space itself is spherical.
Yeah, so
And can you you have a transfer of it from the normal bundle to back to the manifold? You see what I'm saying?
so it's exactly the same.
that's not right?
So
The
this
complexity is the same.
is basically the way to do it, probably.
Yeah.
That's right.
So the real statement of function is that complexity of action on base variety and on normal bundle is the same. So if one is spherical, then the other one is also
Your core normal bundle is probably is in the flag map.
just for any growth.
Yeah.
I am glad for it.
Okay.
Is that a general statement?
Yep.